Hello everyone, and thank you for being here. Thank you for the organizers for inviting us again. It's a pleasure to come to Japan always, and in particular Kyoto. Today I'll talk about what we are doing at PolyPeptide in order to address the ever-present question about sustainability. And I will try to take you through what we're doing. And today we will probably be talking a little more about some early work, some scouting work that we're doing. And basically, I will tell you that this is unfinished work, so we are being very transparent on where we are standing. And really, this is a call for everyone that works with peptides or oligos to really try to address this sustainability with us. PolyPeptide Group, you know, is a CMO or CDMO. I don't need to go into that too much. Let's get into business. The peptide manufacturing industry in light of sustainability, it's an interesting question. It's a very successful area with 22 new FDA approvals. That's a number from 2022, but that's for the preceding 5 years. Business is growing, as you can see on the numbers. There's a rich pipeline. But I think the biggest concern we have is that from a manufacturing and sustainability point of view, some of the indications that we are starting to serve, particularly obesity, requires an enormous amount of peptide. And as a peptide manufacturer, we should be cheering and say, yeah, that's great. But really, it is really not in a good position from a sustainability point of view. There is a conflict between achieving good and green chemistry versus the amounts that we are talking about. Some of the products we make at less than 1 kilo a year. Their sustainability is really not a great issue. But we are going into the hundreds and 500 kilos up to the metric tons, then suddenly it starts to become a significant issue. So what are we doing at PolyPeptide? We have a multi-tiered approach. We do reduce, recycle, replace, and avoid. And we have some examples of how we do things over here. And we're trying to work on a broad platform to see where can we actually find the path to the future. But there are some industrial questions that always hang around. What to develop and what to implement? Are we going for the short-term achievements? We've done that in reducing solvent in the washing of the solid phase. But for having longer-term, higher achievements, really to be more ambitious, we probably need to look at the chemistry. We probably need to look at the entire flow of materials. How and when to implement? Of course, if we could take all our commercial products and just turn them green overnight, that would be lovely. But we are working in a regulated, and some would even say a heavily regulated industry that certainly limits the ability to do those changes. So that in itself is a concern. The industrialization, well, supply chain, availability, material costs, IP restrictions, equipment changes, all of these things come into play when we talk about changing our fundamental chemistries. Something as simple as changing the solvent, we are going typically from a monosolvent like DMF into binary solvents. How are we going to handle that from an equipment perspective? There are many questions that open up that are not just straightforward to answer. And a point that I will be returning to several times during this presentation is that unless there is a general broad adaptation of perhaps even just a subset of these green methodologies, then it is difficult really to make that wave coming. I think those of us who have been working with peptides for a number of years remember how it was that the TBOC was the king before the millennium shift, and FMOC became the king afterwards. That was driven by a single product. We don't see that happening today because it is so prevalent with the FMOC out there. So if we're talking a little about the environmental impact, then a few years ago we did a study on 6 different published processes for making exenatide, a 39 amino acid long peptide. And a little to our surprise, we actually saw that the complete E factor would vary from 4,500 up to 33,600. And this means tons of material per kilo of material that you, kilo of material per kilo of product that we actually get out. So there's a huge variation even within the process for making the same product, depending on your process. And it's really not enough to look at just that. If you look at what does it actually cost in terms of E factor for our starting materials, so the resin, the DMF, the FMARC amino acids, we are talking about 10,000s to 100,000s of true CEFs. So significant amount of material goes into making the products that we do. So we do really think that we need to review our synthesis workflow simply to figure out how can we do this in a better and more efficient way. So we have a few ways. You can say that we can divide it into a disruptive way of thinking, or we can do it in a more conventional way. If we talk about the disruptive part, what is interesting is that, as an example, there's more than 40 amino acid alpha protecting groups for amino acids has been developed. But honestly, today, only 3 are really used. And why is that? Simply because of the lower cost and the larger scale availability. So cost and availability really plays a role in how to select, unfortunately. But that's reality on how to select the chemistry for the future. So how to adopt disruptive methods must be considered from the onset. This is not wasted work. There's a lot of excellent work being done into it. But as an industrialist, we like to see it applied into industry. So with that reality at hand, we decided to say, okay, what can we actually do within the conventional? Have we exhausted what the conventional solid phase, boring FMARC TBOC can actually do? And we wanted to see if we can do more about that. And this is what the rest of the presentation would be about. So we talk about waste prevention, so minimize use in solvents, AAs, reagents, and telescoping. And we're talking about waste management, which is the recycling, the reuse, or the valorization of recycled materials. On the I think this is probably pretty obvious to many of you, but it is, the FMARC TBU still remains the primary way of making the peptides today in the industry. It does consume a large amount of amino acids. Everything is in excess. Typically, sometimes we see processes that have not been optimized, so they will run with 2 or 3 equivalents in excess of everything. We are using the hazardous solvent like DMF, which is going to be somewhat restricted in Europe next year. And we have still the challenges with the chemistry that we are doing. But we still wanted to see if we can actually do something and try to include the waste management in this concept. So we wanted to improve the sustainability while still maintaining the efficiencies, the scope, cost, and an integrated approach. So we went out to see what can we actually do to achieve that. So this is a little, let me take you through this. So we have a few things to consider here. We have some key aspects, which, for instance, is temperature. We need to look at many parameters at the same time. So here's an example of looking at temperature of a simple transformation. You have the FMARC ramage, and you simply treat it with 5% 4-methylpyridine for 5 minutes. What is the result that you get out? Depending on which solvent that you're using, what is the conversion rate, what is the solvent cost compared to DMF, and if you look at the temperature as a third parameter, you can see that in this small matrix here, things vary quite dramatically, and it appears that that the 10% DMSO in ethyl acetate actually seems to be the better one if you accept to run at 50 degrees. So really trying to handle multiple parameters at the same time. The waste recyclability is something that we've considered as well. It's something to be aware of. It's not necessarily that difficult, but it's something to be aware of when you are constructing your new way of doing things. And the simple concept of making sure that if you want to recycle a solvent, that you can actually do it in a reasonable way, which means that don't have two solvents that are too close to each other in boiling point. If you have very high boiling substances, they might be very difficult to recycle efficiently. So there is some logic to that we try to build into the thinking. And with this, we have two examples that I want to go through, and then a small extra one. So we have a non-aqueous FMOC solid phase where we did some recycling and changes and then saw some changes in the hazardous reagent status. And then we have some aqueous solid phase where we included some recycling, some procurement challenges, and also try to address the solubility of FMOC, standard FMOC amino acids in water. So this one is a little busy, but let me take you through it. We did a small study where we made this small AIB ACP peptide, following this methodology up here. 84% yield, 76% purity. Most of the yields and the purities that we're talking about in this presentation will be 70 and above, and that's okay for us because it's screening. We're not talking about an optimization of things. But then we actually went through the waste stream, how can we treat that? So of course the ethyl acetate was distilled away, the oxima was extracted and crystallized. We had a residual 4-MP and other volatiles that were discarded, and then the residual DMSO was distilled. And what we got out of here was that 80% of the waste is ethyl acetate. We managed to do a recovery of 86%. The energy demand is pretty low. And if we should go outside and have that done by a supplier, these cost numbers here are a little old and they were never validated in large scale, but these were just indicative numbers, that it would be a cost of approximately 0.4 euro per kilo. DMSO, you have a high energy demand, but it's only 4% of the waste. You do 70% recovery, and you have a slightly higher cost of the recycling. And oxima is less than 1%, and the energy demand of doing all of that is very high, and you only do a 38% recovery. So perhaps a prudent point would be that, okay, we recycle the ethyl acetate, and the rest we simply just incinerate, but making sure that the incineration process is as green as it can be, so it produces energy like electricity or heat, and preferably with some sort of carbon capture if that's possible. And a reference to a group not associated with polypeptides, you can see that the ethyl acetate DMSO is already being employed in making these peptides here. So that's one way of thinking about it. Now, we keep getting surprises, and in 2019 we had a report from a team at Eli Lilly where they reported that DIC together with oxima actually would form this 5-membered ring, and it would expel the HCN. So that sort of diminished a little the greenness of this system. What it did was that it triggered us to figure out what can we actually do to address that, and we found that solvent selections and even adding scavengers, you can really diminish the presence of the HCN, which was very reassuring. In our plants, of course, we measured whether people were exposed to that, and they came out as blank 0, so that was encouraging, and we couldn't find it in our waste either, actually. Another later report here has shown that the use of an DIC equivalent, TBEC, actually dramatically reduces the formation of HCN, and I don't know why that is, but that is the result. But it triggered another thinking, which was, well, does it actually, should we actually try to look at going into the aqueous phase? And we said, well, you know, this is an exploratory team. This is, you know, you can do crazy stuff, so let's try to see what we can do. The existing technology on aqueous solid phase typically would employ that you would have some modified FMOC protecting groups like the SMOC from sulfur tools. You would have some zirconium or Triton, zirconium. You have some micelles forming. So it has been sort of successful to do it. What we wanted to do was to get back to the original thought is, what can we do with the existing systems? Can we actually tweak them so they start to work under the aqueous conditions? And I should mention here that aqueous is not in water. Aqueous means that you have water mixed with a co-solvent, even for these references here. So we went through, we chose Tentagel. It's really not a favorite synthesis gel of ours, but because we needed to ensure the swelling, we went with Tentagel. And we also found that Polar Clean was doing a good job. Here we have the swelling of water and Polar Clean 1 to 4, and we have some conversion of the chemistry here. Again, a very simple system. So we simply just measure on a simple system how does the chemistry perform. So this was chosen to move on with. The coupling rates actually corresponds to the swelling, and interestingly enough, Polar Clean Neat is really not a very good solvent. We have seen on other solvent combinations that it does something both with the swelling and it does something with the kinetics. So the pre-activation versus the coupling kinetics, they're actually governed by different sort of solvents. DMF just seems to be the one that was the sweet spot for all of them. If we really want to optimize our solid phase chemistry, we would go into different solvent systems depending on what sort of chemistry we were doing, but we don't foresee that happening. So we try to find another next sort of generation DMF system. At some point during our investigations, we exchanged the COMU for the TCFH, and we did that because So following that, we actually with 1.3 equivalent of amino acid, the TCHF and the collidine in water, in Polar Clean and water 1 to 4, we did an 86% purity, above 70% yield peptide. Again, this is just an example of a small peptide, simply to prove the concept of these things working. The next step was to include this little nice step here, where we actually absorb the basic and acidic residuals of the coupling cycle. So, and we do that in a standard mixed bed ion exchange. And so we're actually able to reuse the solvent system here to build the same peptide. And for us, here you have the result here. And for us, it really showed us that we can replace DMF, and we can really challenge the systems that we are working with. Even on introducing something here that on paper nobody really believed in, but in real life it actually worked. And what we saw is that doing that, you can actually, you have a door to drastically reduce your solvent consumption. And then a little adventurous, I would say that, sorry. Yeah, we're still working on that, sorry about that. Then what happened? There was a force majeure declared on Polar Clean. So it went from available on ton scale at €5 per kilo to essentially inaccessible overnight. Really something happened in the supply chain. I don't really want to go into that story. It just tells you that if you have a single source, or even something which is IP protected, you run a certain industrial risk. So what we had to do was basically go back and say, okay, do other solvent systems work the same? And luckily, we were happy to see that we actually find that the NBP, polar-clean, acetonitrile, and DMPU, polar-clean is of course the original one, but these three here actually work pretty well, while the DMSO of some reason fails to give a decent result. So this one was actually quite interesting, because this is the typical solvent that you use in your downstream process. So suddenly we would have a solvent system which by cleaning it through the mixed bed ion exchange, we would have something where we actually do, this might seem crazy to a QA person, but can we actually, within the same process, use the water and the acetonitrile both for the upstream and the downstream? We have not proven that yet, but we don't mind putting it out here as maybe a provocative thought. So on a final note on the solubility of the F-MOG amino acids, in literature in general, it's stated that these are insoluble, and to a large extent that's of course true. But if we do take water and acetonitrile 4:1, water and BMP 4:1, and we add 2 equivalents of collidine, you actually get to what we in the lab today will define as workable solubilities. I don't think that if as Daniel was talking about before, if you have a visual check that everything is dissolved, then you probably will have problems with your robot. But we do know that when we add things like this, then of course it will be dissolved as you consume it. It is only at 0.1 molar, so a little less or half of the concentration that we normally use, but it's workable, and it gives us a good entry and a good platform to actually move, to say that maybe there's something that we should work more with. The next thing we want to talk about is catalytic solid phase. Again, something which is on the sketchboard with us. We have published a few parts of it, and we want to bring it out here, and in the end you will see why. But the concept of catalysis is really not new. It's pretty obvious. So where could we actually do? So today there are a few catalysts out there. These seleno compounds here have been published. And again, going back to our mantra, what can we do with the existing systems? So this is great work, but we really wanted to take a step back and say, what can we do with the existing systems? So we did a 2-step approach. First, we wanted to do a proof of concept, and then we, of course, want to do some further studies later on. So right now, I'll do and present you the proof of concept. So if we look at where can we actually find the catalytic elements in a solid phase synthesis, it's pretty easy. We have the base here, and we have the coupling additive. So that would be the oxima or the HOBT. And so we wanted to look for those. And we did some screenings, again, very simple systems. Here it's just one coupling. The 20% oxima, mole percent of oxima turns out to be the best one here. We did a 5% scan with all of the different coupling aids here. HOCT turned out to be the better one there, so we continued with that. Please note that we use DMF here. Then we went with the HOTC system, we went into scanning all of the different greenest solvents. And you would see that the NBP ethyl acetate 1 to 4 came out best here. And basically we did the same scan with the bases. Here's the number of bases that we looked at. The story is very easy. DBU is the only one working. And you can see here that with a 5 mol% of DBU, we can achieve a AC3% conversion with the DMSO ethyl acetate, or 75 with the NBP ethyl acetate. So in the end, we did a screen. We did this peptide up here because it has been published as an aqueous equivalent. And following entry 7 here, treating it with 3 times DBU at 1 hour, and then doing the coupling with HOCT and DIC. We're using a single wash because we don't have a lot of material to remove. And then we come out with a pretty good purity here, and again in yields above 70%. Final slide here. We have some work to do on the racemizations. So obviously changing the coupling conditions will generate different levels of racemization. Of course, we believe that the presence of the oxazolone here is the key for the racemization. And so how to limit that, how to find that balance is work for the future. So in summary, we try to do a broad adaptation of the circular economy. So reuse, redo, don't throw anything away. Make sure that every material is used again. We want to have the waste recyclability, and we want to do that already in design of the new structures or the new manufacturing platforms. We do believe that the aqueous system is not scary at all, that we can work with it based on our preliminary systems here. And again, this is unmodified F-MARC amino acid. It's the one that we get in hundreds of kilos. And finally, we have started to look at the catalysis of the solid phase, again, just not using so much material in the processes. One thing which is very close to our heart is this work here. So PolyPeptide is really open to any collaboration that you may want. So pop by the booth or take my email at the end of the presentation, and we'll be happy to entertain any discussion on that. Finally, Jan Paulus is a guy in my team. He's driven when we talk about sustainability, and he's really a key person in our efforts here. And finally, I want to thank you for your attention.